Welcome to part 3 of this series of videos describing the implementation of dissolution analysis in Statgraphics Centurion version 20. This discussion has been divided into 3 videos. Part 1 dealt with fitting dissolution models. Part 2 covered model-dependent comparisons using those fitted models. This video, part 3, deals with comparing test and reference batches without fitting any models. Our sample data involves a reference batch and 5 test batches. Dissolution measurements were obtained at 4 different time periods using 12 units. To perform this analysis using Statgraphics version 20, select Relate from the top menu, and then on the far right in the Dissolution Analysis section, select Model-Free Comparisons. On the first dialog box, I will indicate that the data from the multiple units has been placed in multiple data columns. Instead, all dissolution measurements could have been placed in a single column and code columns created to identify the units. On the next dialog box, I'll indicate the column containing the batch identifiers, the column containing the times, and the columns for the units. This is the output created when the procedure is run. You will see that each of 5 batches, test 1 through test 5, has been compared to a reference batch. The statistics computed include F1, F2, bootstrap limits on F2, an indication of whether or not there were large coefficients of variation, and then near the bottom, a Mahalonobis distance, Wellek's t-squared EQ, and a p-value for t-squared EQ. Any row in which you see either a statistic or a p-value highlighted in red indicates that that pair of batches, that test batch and that reference batch, cannot be declared to be equivalent. The first statistic calculated is the F1 difference statistic. F1 compares the differences between the means of the test batch and the reference batch at each time period. Equivalence between the test and reference batches typically requires that F1 be less than or equal to 15. A second very popular statistic for comparing the test and reference profiles is F2. You can see the definition of F2, which depends upon the differences between the means of the reference and test batches at each time period. Equivalence between the test and reference batches typically requires that F2 be greater or equal to 50. To calculate confidence limits for F2, bootstrapping is used. In bootstrapping, multiple subsamples are created by selecting observations with replacement from the test and reference batches. The value of F2 is calculated for each subsample. The 5th and 95th percentiles of the bootstrap F2 values form the confidence interval. Equivalence between the test and reference batches is asserted if the lower 90% confidence limit for F2 is greater than or equal to 50. As you can see here, according to the lower 90% F2 bootstrap limit, the test 1 and test 3 batches are equivalent to the reference batch. A drawback of F2 is that it may not lead to a good decision if the variation amongst measurements from the same batch at the same time is too large. Statgraphics computes the coefficient of variation for each batch time combination and flags any F2 values for which either batch, the test or reference batch, had a coefficient of variation exceeding a specified value at any time period. The limits for the coefficient of variation are set by the user, and usually there's a different limit at early time periods than for later time periods. In this case, the maximum allowable coefficient of variation before 90 minutes is 20%. At 90 minutes or later, the maximum allowable CV is 10%. In cases where one or more CVs are high, the comparison may instead be based on the multivariate distance between the mean vectors for the test batch and the reference batch. Mahalonobis distance is defined by d equals the square root of that matrix product that you see. It involves the variance-covariance matrix of the dissolution measurements. Equivalence would be asserted if d was no greater than it would be if the means of the test and reference batches differed by 10 in the same direction at each time period. Wellek developed a method for calculating a p-value based on the Mahalonobis distance in order to test for equivalence between the reference and test batches. His equation for t squared is shown here. T squared is then compared to a non-central F distribution with a non-centrality parameter that depends upon an equivalence margin called delta squared. Often, delta squared is set equal to 10. For the t-squared test, equivalence is asserted if the p-value is less than or equal to 5% for a specified equivalence margin. Here, only test 1 has a p-value that doesn't exceed 5%, so only test 1 can be asserted to be equivalent to the reference batch.